this is the lecture number 20 for module 4, where actually we are discussing constitutive relation 2. So, in the previous class we have learned that how to relate the mathematical engineering mathematical constants of the constitutive or compliance matrix, which is Cij or Sij, in terms of the engineering elastic constants or engineering constants, which are Poisson's ratios and the Young's modulus or the coupling coefficients. So, now in this lecture, what we will learn is that is these engineering constants or engineering material constant or engineering elastic constants have any restriction on the on their values. For instance, some of you probably know that the Poisson's ratios cannot be greater than half and cannot be less than -1. This is probably you have learned in your strength of material or solid mechanics course. But what would be the case in case of a large number of Poisson's ratio? For instance, the orthotropic material, there are 3 Poisson's ratio. What is such restriction? So, is that Poisson's ratio for such material will have the same kind of restriction, or it is having something different? So, and similar to that, you have also learned probably that the shear modulus and the Young's modulus will be always greater than 0. So, and how these relations comes? So, we will see this in from this lecture. So, before doing that, let us quickly recap that we will start with the orthotropic material. For instance, the constitutive relation for the orthotropic material can be written in this, and this is the strain energy function. Now, probably in our previous class we have discussed that strain energy function, that u should be greater than 0. If u is not greater than 0, then what will happen? That it will not produce a physically meaningful deformation. So, meaningful stress or deformation, whatever you say. So, now so we know the strain energy density should be greater than 0. Now, this strain energy density, if this is greater than 0, so we know the form of the strain energy, which is half of epsilon transpose C epsilon, which is essentially the vector format, the void notation, where epsilon is essentially this is here the epsilon, and C is this matrix. So, now here in the tensorial notation, though this C and this C look same, but this is a 4th order tensor, which is Cij KL. So, now half of epsilon contraction or epsilon inner product C, inner product epsilon. So, which gives me the scalar function. So, this we know from our tensor algebra knowledge. So, this quantity has to be greater than 0 for a realistic deformation or the realistic stress, whatever you call. Now, to have this condition, so to have this condition satisfied, this can be for any strain. So, this finally leads to this component or the C component C matrix, which has to be the positive definite matrix. So, unless this quantity is or this matrix is a positive definite matrix, this cannot be greater than 0 for any epsilon, or here that C should be positive definite matrix. Unless C is positive definite matrix, for any epsilon this quantity cannot be greater than 0. So, similar to this, actually we can have from the compliance relation, which is epsilon and stress, how it is related. So, we can also just substituting C inverse, and then we can also say that half of sigma transpose is sigma, or in a tensorial notation here remember that S is Sij KL, which is a 4th order tensor. Here it is a Sij. right. So, now with this this quantity has to be 0 greater than 0. So, this if had this quantity has to be greater than 0, then this matrix S, this matrix S has to be the positive definite matrix. So, this actually imposes some restriction on these Sij and Ci, finally Cij. Now, if there are some restriction on the Cij and Sij, then finally we can put this restriction on the engineering constant, Poisson's ratios and the Young's modulus and the shear modulus. For instance, before discussing those issues, let us see what does this mean, that positive definite matrix. So, for instance, a positive definite matrix, a real symmetric matrix C to be positive definite if and only if. So, necessary and sufficient condition if. So, sometimes it is written in terms of IFF. So, IFF, so it means if and only if, and then necessary, and it means necessary and sufficient condition. So, following conditions are satisfied. So, for any non-zero vector epsilon, so this epsilon transpose C epsilon should be greater than 0. So, for any non-zero vector, now if epsilon is a 0 vector, naturally this is equals to 0. So, which is not the case we are looking for. So, epsilon transpose C epsilon is greater than 0, and then all eigenvalues of C which is lambda I should be greater than 0. So, probably all of you know the eigenvalue analysis. So, the all eigenvalues is greater than 0, and all upper left submatrices of Ck have positive determinants. So, what does this mean? This means that suppose let us do it for 3 by 3 matrix. So, which is C11, C12 and C13, C22, C23 and C33, suppose, and this is symmetric. So, this means that means that C11 should be greater than 0, C11 into C12 minus C12 square should be greater than 0, and determinant of this C matrix should be greater than 0. That means, essentially this part is greater than 0, determinant of this part is greater than 0, and finally the 3 cross 3 determinant of 3 cross 3 should be greater than 0. So, now in addition to that, all pivots without any row exchange are greater than 0. So, those who have know Gaussian elimination method, they know what is pivots. So, if you do a row reduced echelon form of a or reduced row echelon form of a matrix, then you get the pivots. So, these pivots cannot be negative. If the pivots are negative, then the matrix cannot be said as a positive definite matrix. So, in a summary, so a positive definite matrix is a matrix which is a real symmetric matrix. Obviously, it is symmetric matrix and it is a real symmetric matrix. So, we are talking about real case only, we are not talking about the Hermitian case here only. So, here that epsilon transpose, or for any vector, any non-zero vector epsilon, it is greater than 0, that is first condition. All eigenvalues of that matrix should be greater than 0, and all the upper left submatrices, that is C11, C12, C22, and this first submatrix, this is the second submatrix, and this is the full matrix since it is a 3 cross 3 matrix. So, this will have the positive determinant, and then all pivots without any row exchange, this should be keep in mind that it is without row exchange. If all pivots are greater than 0, then the matrix is said to be a positive definite matrix. So, finally, why we are discussing this? Because if this matrix C is a positive definite matrix, we get this condition automatically, and in the previous slide we learned that our strain energy U has to be greater than 0. So, this is essentially implies this condition. So, let us see with an example. Suppose there is a vector a, b, c, and this is a matrix, and then if I take the transpose of this vector a, b, c, components are a, b, c, and then multiply, and then again multiply the vector, then we get this quantity. Now, you see carefully, this is a square term. So, irrespective of the value of a and b, this quantity will always be greater than 0. Now, similarly, b and c, irrespective of value of b and c, this quantity will be greater than 0. Similarly, c is a square, so this is greater than 0. So, whatever be the vector of a, b, c, this quantity, finally this quantity is essentially say this vector is epsilon. So, epsilon transpose c epsilon, this quantity is essentially greater than 0. That means, what it means mathematically is that for any vector here, this quantity will be greater than 0. Now, what it means physically for us? Physically for us is whatever be the form of the strains, this strain energy epsilon transpose c epsilon half multiplied by the half, whatever be the case of epsilon or the strains or the strain states, the strain energy has to be greater than 0, and this will be greater than 0 only if c, the quantity c, is positive definite matrix. Only then this can be satisfied. Otherwise, if C is not a positive definite matrix, we cannot ensure that the strain energy density is greater than 0. So, based on these criteria will actually derive the restriction on the material constants. So, let us see how we can use these concepts. Suppose, so this is from our previous class that constitutive matrix. Finally, our objective is to pose restriction on these engineering constants E and nu and shear modulus G. So, finally, we know how these mathematical constants are related with the engineering constants. So, similar to that, we can write the compliance relation also in terms of engineering constants, which are this. So, now we know there are 9 independent constants. So, there will be this can be this is the orthotropic material. So, now with this in mind, let us derive the restriction on the engineering constant. Suppose we test in the previous lecture we have seen we give a normal stress in one direction. So, which is sigma 1. So, now this sigma 1 will results in epsilon 1 is a 1 by sigma 1 by E 1. Now, based on the sign on the sigma 1 actually, then epsilon 1 has to be the positive. This is a very understandable thing, because if epsilon 1 is negative, then if you stretch the material, then it will not it will compress, which is unphysical here. So, similar to that, other components if I give, except sigma 1, I give other directions separately, and then we can say that these the diagonal of the compliance matrix or the S matrix, the diagonal of the compliance matrix can be all diagonal entries are greater than 0. So, similar for the shear cases also, S 11 to S66. So, which is essentially S11, if S11 is greater than 0, that means 1 by E1, and so E1 has to be greater than 0. So, E1 cannot be negative. So, E1 is greater than 0, E2 is greater than 0, E3 is greater than 0, and then shear modulus are greater than 0. So, you see from the 9 independent constant, we can we have already found out the restriction of the 6 independent constant, which is E1, E2, E3, G12, G13 and G23. Now, from the now if you remember the diagonal entries of the constitutive matrix or the stiffness matrix C, then we can also say that this quantity will be greater than 0, this quantity will be greater than 0 and this quantity will be 0. Additionally, this determinant of delta will be has to be greater than 0. So, if you remember that which is essentially 1 C11 is essentially 1 minus nu 2 3 by into nu 3 2 by E2 E3 into delta. So, E2 E3 we have already proved greater than 0. So, this quantity should be greater than 0 and this quantity should be greater than 0. So, similar to that other diagonal entries if we compute for C11, C22 and C23. So, these quantities will be greater than 0. Now, what it means actually for us, let us see. So, if this greater than 0 means what restriction it poses. So, suppose I take this and analyze it. So, suppose this is greater than 0, it means that if I substitute in place of nu 2 1, if I substitute the reciprocal relation, we know the reciprocal relation which is nu I j by nu j I equals to E I by E j. We have learned in the previous class, this is the reciprocal relation of the constitutive matrix in terms of engineering constants for an orthotropic material. So, if we do that, then if you substitute it, then this becomes greater than 0. So, now if you just do the some manipulation, that is nu 1 2 square is essentially E1 by E2 and then you take the square root essentially. So, mod of nu 1 2 should be less than E1 and E2, the ratio square root of the ratio E1 by E2. Similarly, we can instead of nu 1 2 substitution, we can nu 2 1 substitution in terms of nu 1 2, we can substitute nu 1 2 in terms of nu 2 1, which will give me this relation. So, essentially you see that Poisson's ratio cannot be arbitrary actually. So, Poisson's ratio can be from here, that Poisson's ratio can be negative also, but mod of this Poisson's ratio should be E1 by E2, square root of E1 by E2, it should be greater than this. So, Poisson's ratio should be less than this. So, similar to that, if I use this relation and this relation, I will get this, this and this. So, you see this relation, this poses a restriction on the Poisson's ratio given the E1 and E2. That means, Young's modulus and if I give the Young's modulus in the 3 axes, so I can have a proper restriction on the Poisson's ratio of the orthotropic material. Now, we will see what this condition means. So, let us go for this. So, the determinant of delta should be greater than 0. Now, determinant of delta should be greater than 0 means if I express the determinant, so it will be this. This should be greater than 0. Now, if I do some manipulation, I take this term this side and then I take 2 down here. So, this new 1 3 1 2 1 and 3 2 should be greater than this. Now, if I again use the reciprocity relation, then nu 1 3, nu 2 1 and nu 3 2 will be nu 2 1 square E1 by E2, nu 3 2 square E2 by E3 and minus nu 1 3 square E3 by E2, E3 by E1. So, divided by 2. Now, see these quantities, since E1, E2, E3s are greater than 0 and these are the squares. So, this finally gives me the restriction that product of all 3 Poisson's ratios should be less than half. So, this actually says that Poisson's ratios cannot be arbitrarily large. For instance, one of the Poisson's ratio is very large, other one has to be less, otherwise this condition cannot be satisfied. So, the Poisson's ratios cannot be arbitrarily large. This poses the restriction on the Poisson's ratios, but there is a thing, if one of them is negative, then actually on the other two there is no restriction. So, this we can observe from this relation. Now, again what this means for the transverse isotropic material. For instance, for the transverse isotropic material, if we assume the 2-3 plane is symmetry plane, again with this this plane of isotropy is this is the plane of isotropy, 2-3 plane. So, if we assume that we know what are the material constants for this transverse isotropic case, which is E1, E2, E2 nu 1 2, G2 3 and nu 2 3. So, if we assume this transverse isotropic case, then if we we know from our previous discussion that E1, E2 and G23 will be sorry G 1 2, it will be not G23. So, these quantities will be greater than 0. Now, then what is the restriction on these nu 1 2 and nu 2 3? So, suppose I assume that this is the condition, E2 and E3 are same. So, I assume it is E and E1 is E dash, and then nu 1 2 and nu 1 3 which is equal for the transverse isotropic material, which is nu dash, and then for the in plane that x2 x3 plane, the isotropic plane Poisson's ratio is nu. Now, if we use this relation, which is we have seen from the orthotropic case, we can prove that in plane case for the plane of isotropic, the Poisson's ratio should be -1 to in between -1 to +1. So, now similar to that, if we use these two relation and then substitute this E and E dash. So, if you substitute this, you will get this, and then you will get first this, and then if you substitute this, you will get this. So, this relation actually again poses some restriction on the nu dash, that is the other Poisson's ratio. Now, if we again use the previous case, that is the this quantity, that nu 1 3, nu 1 3, nu 1 3, nu 2 1 should be less than half, then we can just substitute these two Poisson's ratio, which will look like in this form, and then again if we include this here, then again we will get this. So, this is a very stringent restriction compared to this. Now, similarly, so that what it means, that the material constants is essentially the engineering constants cannot be arbitrary. So, this arbitrariness, non-arbitrariness is coming from the positive definiteness of the stiffness matrix, and this positive definiteness of the stiffness or the compliance matrix implies some restriction actually on the engineering constants. And so, if we again choose the isotropic material, where this is this E dash equals to E and nu dash equals to nu, then this will actually lead to the result we already know from our strength of material knowledge. So, essentially what we have learned? We have learned that we can represent engineering constants with the mathematical constants, and then we can pose some restriction on the engineering constant as well as mathematical constants. For instance, if I if you have seen the, if I consider a 2D case now. So, for instance, for a 2D unidirectional material, so orthotropic material, which is essentially say C11, C12, 0, C12, C22 and 0, and then C66 and then 0 0. So, this is the in case of a 2D material. So, these are represented in terms of engineering. This can be also represented in terms of engineering constants. So, C11 essentially from our positive definition, this is my C matrix. So, this C matrix has to be the greater than means the C matrix has to be the positive definite matrix. So, to become a positive definite matrix, it is all eigenvalues has to be greater than 0, and then for any vector these all those 4 conditions of positive definite matrix is always there. Beyond that, I can also say the third condition, which is C11 should be greater than 0, and then C11 C22 minus C12 square should be greater than 0, and then C66 into C11 minus C22 into C22 minus C12 square, this has to be greater than 0. Now, using these also we can pose this restriction. For instance, we can find out that C11 is actually E1 by 1 minus nu 1 2 into nu 2 1. So, similarly, this G 2 2 G 1 2 is essentially C 6 6. So, with this also we can find out G 1 2 here. So, C 6 6 is G 1 2. So, with this also we can pose the restriction on the engineering constants. But essentially in a summary that all Young's modulus and all shear modulus will be greater than 0 because of the positive definiteness of the matrix, and the Poisson's ratios, there are for the isotropic material we know this, for an transverse isotropic material also we know this, and for the orthotropic material, that is nu the product of 3 Poisson's ratios should be less than half, and then the Poisson's ratios, mod of the Poisson's ratio should be the square root, that is mod of ij should be less than ei by ej to the power half. So, this condition is also implied. So, if you remember these things, we can actually say that a material, a given engineering constant, a material actually represent the physical material in real world or not. So, that is the basically idea. The idea is essentially that we need to model the material or we need to model the material mathematically. We need to choose the intrinsic properties of the material and how these values will choose. So, this has to be some restriction on those intrinsic values. So, this says some ways of representing those conditions. So, in the I stop here today, and the next class we will discuss, the next class is the last class for this module. So, in the next class we will discuss the properties of lamina or some aspects of the lamina. Thank you.